Today's lesson starts us graphing inequalities in two variables. Now last year in grade 10 we would have graphed in one variable just on a number line, but now we're going to be graphing inequalities that contain both an x and a y variable. Now we're going to start off by actually again refreshing our memories on the differences between equations and inequalities, because they are a lot different when we talk about these in math. So the first off we're going to talk about are the equations. Now, equations, when we go and solve them, and that's what we've been working with a lot so far this year, equations are functions that have definite solutions. So when we get to the end of solving, we can say, you know what, we know that x is 6, or we know that x is either plus or minus 2, or x is 3 over 7. We have a definite answer. And equations have an equal sign, as shown right here. So equations do have an equal sign, and that would give us a definite solution when we solve, because x would equal a certain value. We're going to contrast that with what inequalities are. Now for us, inequalities are going to be a lot more to talk about. Inequalities now will have an infinite number of solutions. We can't even name them. There's just so many that we can't even represent them all. So we're saying, instead of having an definite answer, we now have a solution region. So we look at all of the solutions that are out there as one piece of information. So the solution region on the graph would include a boundary line, and this boundary line separates the graph into parts that are solutions and parts that aren't the solution, and that line itself may or may not be part of the solution. And just to say, contrast it a little bit with equations, where equations had equal signs, inequalities have the inequality signs. They have the greater than, less than, greater than or equal to, or the less than or equal to sign. So equations have a finite number of answers, and inequalities have an infinite number of answers. We can't even describe them all. So you might need to pause the video to get those notes down, but we're going to move on to our first example. This first example is a two-part question. First off, it's saying graph the inequality 4x plus 2y is greater than or equal to 10. And then the second part says, once you have it graphed, can you determine or verify if the point 13 is part of that solution? Does it lie in the solution region, or does it lie outside of that solution region? So we're going to start this question by actually going back to a grade 10 skill. We're going to start with this inequality. And we should be able to represent this or identify this inequality as being a linear function. There are no exponents, so when I graph this, I'll have a straight line. And that straight line creates that boundary line that I talked about earlier. To do this, we want to take this equation, 4x plus 2y is greater than or equal to 10, and we want to change that back to this form we looked at in grade 10, y equals mx plus b. Because mx plus b was called the slope y-intercept form, m being the slope, b being the y-intercept. If I can do that, I can graph the line. So we're going to use some algebra, and we're going to isolate the y. First step, take away a 4x. When we do that, we're left with 2y is greater than or equal to negative 4x plus 10. So now you can start to see that it's actually getting into that mx plus b form. The only thing stopping us is this 2 on the left-hand side. So we now have to divide that 2 out, divide the 2 out of both sides, and we're left with y is greater than or equal to negative 2x plus 5. So that 2 divides out of both of those terms on the right-hand side. So now here's our inequality that we're going to graph. And to do it, like I said in grade 10, this is our m. So our slope is negative 2, which tells us this line goes down to the right. Our y-intercept now is at 5, or more specifically, 0, 5. So we can graph this now on the graph paper to the right, and we can come up with our solution. So I'm going to plot the y-intercept first. It's at 0, 5. So 0, 1, 2, 3, 4, 5. There's my y-intercept. Now my slope is a -2. Remembering the science definition of slope being rise over run, -2 means I rise -2. That means I go down 2, and I go over 1. So here is the new point. I have 2 points. I can create this line. Now, before I go, we have to know if this line is actually included in the region or not. I go back to this inequality, and right here, it's saying greater than or equal to. This or equal to part means that this line that I'm about to draw will be part of my solution. So that means I have to draw a solid line between these points. So my points will be connected, and this extends beyond. So here's my solution. There's the line, that's the boundary line. The points on that line will also make this inequality true. So now we have to go and we have to consider what the inequality is actually telling us. The inequality says greater than. To be greater than this line, I have to be in this area here. All of these points are above that line. So this becomes my solution region. This is the region that has all those infinite number of solutions that we talked about in inequality having. So in here, this shaded region becomes all of my answers. Now the second part of this question asks us, is the point 1, 3 actually part of this solution? Now I could go on my graph and say, here's 1 over 3 up. It's right there. Is it part of it? Well, we already determined that it's greater than or equal to, so if it lies on that line, it's part of my solution. But let's prove it algebraically. The inequality we were looking at was 4x plus 2y is greater than or equal to 10. And we're checking the point 1, 3. This is x, this is y. So I could put it in and verify. So I can say 4 times 1 plus 2 times 3, that's my x and y, should be greater than or equal to 10. That's 4 plus 6, greater than or equal to 10. Is 10 greater than or equal to 10? Well, yes, it's equal to 10. So the point 1, 3 is part of the solution. And everything else that we had highlighted in that yellow region would also make this inequality true. So let's move on to another example. Here's the next example. Same sort of thing. It's saying graph 5x minus 20y is less than 0 and verify the solution region. So again, we're going to start with this inequality. And we're going to get this into slope y-intercept form, or y equals mx plus b. This question is kind of going to cause some problems because of this minus y. So what I would suggest, whenever you see a minus y in an inequality, move it first. So I'm going to add this 20y to both sides. So I get 5x is less than a positive 20y. Now I want to isolate the y, so I divide out a 20, divide out a 20, and I get 1/4 x is less than y. Now when we look at inequalities, we always want to have the y to be on our left-hand side. So I'm going to go and say, well, if I put my y on the left hand and the 1/4 x on the right hand, if I examine what the inequality said before I moved them, it's actually saying y is greater than a 1/4 x. So when I rewrite it, I need to make sure that my sign still represents that. So my inequality now becomes y is greater than 1/4 x. Now again, this is slope equals y, or mx plus b form. So my slope is a 1/4. And out the back, I could say plus 0. So my y-intercept, in this case, is 0, 0. So I have a positive slope, it's going to be going up to the right, and I have a y-intercept at 0, 0. So I can start by graphing this. I'm going to go over here and say, here's my y-intercept at 0, 0. Slope, rise over run, means go up 1 and over 4. So up 1, over 4. Here is the other point. And I need to connect these lines. But again, I need to look, is this line part of my boundary? Is it part of my solution? So if I'm looking at the inequality on the left-hand side, right here, this says, my solutions are just greater than this line. It doesn't include the line. It doesn't have or equals to. Since this is just greater than, we represent the line as a dotted line. So a dotted line tells us that this is the boundary, but it is not included in the solution. So I go back, connect these with a broken or dotted line. So that's going to divide my graph into a solution region and a non-solution region. But this says that my solutions lie greater than this line or above this line. Above the line, we should shade this region. Above the line is all of this stuff. So all of this, anything, any point within this highlighted or shaded region becomes an answer that would make this inequality true. Now, if you look, the question actually asked us to graph it, which we just did, and it also says verify that solution region. So that means pick a point within that solution region and make sure that it actually makes sense. So if I was to look at my graph, I'm going to pick a point that I know for certain lies within there. So if I look, I might as well stay somewhere like here. I know for sure that this point is in the solution region, and this point is 0 over and 4 up. So I'm going to verify that 0, 4 actually keeps this inequality true. So to verify that solution, I go back to my original equation, or inequality in this case, which was 5x minus 20y is less than 0, and I want to make sure that 0, 4 works. So that's going to be 5 times 0 minus 20 times 4 better be less than 0. Well, I get 0 minus 80 is less than 0. Negative 80 is definitely less than 0, so I did shade the right part. Something within that solution region would make the inequality true. So some takeaways from this first part of this graphing inequalities in two variables. If I have greater than or less than in my inequality, my boundary line would be dotted or a broken line. If I have greater than or equal to or less than or equal to, my boundary line is a solid line. The other thing we should represent, or we should talk about, is that I'm asking greater than or equal to, we would be shading above the line. If I'm saying less than or equal to, we would be shading below the line or the boundary line.